All right, this problem involves Newton's law, and it has this pendulum that's swinging, and at this instance it's 30 degrees from the vertical. And the pendulum is swinging, so it has some curved path, sort of like this. And this means it's going to have some normal component of acceleration and tangential component of acceleration. We're given that the tension in the string is equal to 2.5 times W, and let's just make this more clear that it's connected to some structure. So we're asked to find its velocity, and we're asked to find its acceleration. The first thing we should do is we should draw a free body diagram of this, and we're going to use its normal and tangential components as coordinates. So we're going to have NT coordinates, and we know that its normal force points back inside, so this becomes the normal coordinate system, and we're going to say this right here becomes the tangential coordinate system. And what do we know? Well, we know it's going to have a tension force that is along this normal coordinate, and it's going to have a mass times gravity force. It's mg that is acting straight down. And we know that this right here, this is 30 degrees. And we can extend this normal line a little further. We know this weight acts straight down, so this right here is also 30 degrees. And we want to draw its kinetic diagram. And so for its kinetic diagram, again, it's going to have its normal direction, its tangential direction, and we're going to assume that it has both of these accelerations in the positive direction. So it has a mass times a normal acceleration, and it has its mass times a tangential acceleration. And we know that the normal acceleration is its velocity squared divided by rho, which is its radius of curvature. And I forgot to put what this radius is in this problem. It is 2 meters. But now since we're not dealing with x-y coordinates, and we're not summing our forces in our x and our y direction, we have to sum our forces, sum the forces in our normal direction, and that's going to be equal to a mass times the acceleration in the normal direction, and we have to sum our forces in the tangential direction, and that's equal to a mass times an acceleration in the tangential direction. So let's do this. And if we sum our normal forces first, well, we have this t right here. This is t. We have t, it's going in our positive direction. We define normal, the positive direction to be up. So we have t. And then we have to come up with this component of this mg. And so what will this be? This will be its cosine. This right here is going to be the cosine of mg. So minus mg times the cosine of 30. And this is equal to its mass times its acceleration in the normal direction. And we'll leave it for that as that right now. Now let's sum the forces in the tangential direction, and we have, so if this is the cosine, then this direction right here is just the sine, and we just have mg times the sine of 30, the sine of 30 is equal to mass times an acceleration in the tangential direction. Now, look at this. Right here, our mass, we weren't given anything, but It's in both sides of the equation, so it can just cancel right out. And now we have this. We have the tangential acceleration is equal to g times the sine of 30. And we know gravity, because we are in SI units. Gravity is equal to 9.81 meters per second squared. We can evaluate this expression and we get our tangential acceleration is equal to 4.9 meters per second squared. So how do we deal with this normal part of the acceleration? Well, right here we're giving that this tension in the rope is equal to 2.5 times the weight. And what is the weight? The weight is just mass times gravity. So this tension force is equal to 2.5 mass times gravity. And if we substitute this in for t, we have 2.5 mass times gravity minus mg times the cosine of 30 is equal to a mass times an acceleration in the normal direction. And again, look, there's a mass here, a mass here, and a mass here that all cancel out, and we're just left with an expression that we can evaluate. So we get our normal acceleration is equal to 16.03 meters per second squared. And this is good. This is what we need. So our total acceleration, our complete acceleration is equal to the square root of our normal component squared plus our tangential component squared. And this is equal to 16.03 squared plus 4.9 squared. And this number is equal to 16.76 meters per second squared. So this is our acceleration. And what angle does this occur at? Well, we know that. All right, so now we have our acceleration. Let's try to figure out what our velocity is. Well, right here we have an equation for velocity. We know that, let's get a different color. We know that our normal acceleration is equal to our velocity squared over rho. And rho is our radius of curvature. So our velocity squared is equal to our normal acceleration times rho. And our velocity is equal to the square root of our normal acceleration times rho. And we have our normal acceleration, we have what our radius of curvature is. So our velocity is equal to the square root of 16.03 times this 2 meters right here, this radius. And when we do this, we get a velocity is equal to 5.66 meters per second. So there you have it. Your acceleration is 16.76 meters per second squared, and your velocity is 5.66 meters per second.